Assalamualaikum and a very good day. For the project, our topic is mass spring damper system. Mass spring damper model consists of discrete mass nodes throughout an object and interconnected via a network of springs and dampers. The objectives of our study are to explain the concept of mass spring damper system, to solve the second order linear differential equation of mass spring damper problem by using Laplace transform manually and by computer-aided solution. And lastly, to study the maximum displacement of the mass that will be attained.
Next is mathematical model. The figure shown in the slide is a damped mass spring oscillator system. The system consists of a mass of 0.25 kg attached to a spring. The stiffness of the spring is 4 Newton per meter and the damping constant is 1 Newton second per meter. The mass is displaced 0.5 meter to the left and the initial velocity is given 1 meter per second to the left. Then the initial value problem for the system is 1 over 4 of second derivative of y with respect to t plus first derivative of y with respect to t plus 4y of t equals to 0, where the initial condition given is y0 equals to negative 1 over 2 and y prime 0 equals to negative 1. Note that the negative sign for the initial conditions reflect the initial displacement and initial velocity are to the left.
Next, we proceed with the manual solution. In the manual solution, there are few steps need to be taken in order to get the maximum displacement. This is the initial value problem with the initial conditions that we get from the equation before. Step 1. We need to convert the initial value problem into initial value problem for the system in a normal form. Then, substitute equation 3.1, 3.2, and 3.3. Thus, we will get the initial value problem with the initial condition. Step 2. We need to perform Laplace transform on equation 3.5 and 3.8 to obtain y1 with respect to s and y2 with respect to s. These are the calculation. For step 3, we need to substitute 3.11 into equation 3.12 to obtain y1 with respect to s. And then we will get this. Step 4. We have to perform inverse Laplace transform on equation 3.13 in order to get the general solution. The general solution is negative 1 over 2 exponent power of negative 2t cos 2 sec 3t minus 1 over sec 3 exponent power of negative 2t sin 2 sec 3t. Step 5. We perform differentiation on equation 3.14. We set the equation 3.15 equals to 0 in order to get the value of t. Substitute the value of t, 0.096, into equation 3.14 in order to get the maximum displacement. We will get the maximum displacement as 0.55 meter to the left of equilibrium.
For the computer-aided solution, we use Jupyter Notebook software to solve the system of ordinary differential equation and to ensure the results in manual solution. So, the first thing we need to do is, we have to import and define some of maths modules and package, and we define the differential equation of y1 and y2. After that, we can get the general solution and find the constants value. We substitute the constants value into equation of y1 and equation of y2. After that, we can find the value of t. Based on that value, we can find the maximum displacement. Last but not least, we plot the graph. So, based on this plotting graph and the calculation in the manual solution, we obtain the maximum displacement of the mass. It occurs to the left of equilibrium, which is 0.55 meters at 0.096 seconds. Furthermore, based on this graph, it is interesting to observe that the graph of yt is closely but not exactly touch the exponential curve. Therefore, it can be concluded that the system oscillates, but the amplitude of the motion decays exponentially.
As a conclusion, the system shows that the damping works on the system to reduce the kinetic energy and to slow the frequency as well as the amplitude. Hence, based on the model in our study, it recommends to increase the damping coefficient B in order to get critical damp motion. So, the system return to equilibrium rapidly and remain in equilibrium as well as compared to underdamped and overdone system. That's all from us. Thank you.